Next, let's look at how to graph a piecewise defined function. And if you recall, this is the function that we look at in the previous lecture. So how I would suggest doing these is graphing the pieces separately and then putting them all together in the graph. And with time, you can graph it straight on the same coordinate plane. So notice that we have three pieces. So the first piece, second piece, and third piece. So the first piece is a parabola. So it's going to be a parabola. So x squared plus 2x, and I can factor out an x. And some characteristics of this parabola is that the x-intercepts are at 0 and at -2. So it's going to cross the x-axis at 0 and at -2, -1, -2. And then where is the vertex going to be? Recall from previous knowledge that the vertex happens at -b/2a, where this is your a, this is your b, and your c is 0 in this case. So -b, so -2/2 times a is 1. So the vertex happens when x is -1, right here. And what would be the y value of the vertex? It would be the function evaluated at -1. So when I put -1 in here, I would get that the y value of the vertex, so this is the x val, and then the y value of the vertex will be -1 squared plus 2 times -1. So this is 1 minus 2, so it's -1. So the vertex is as -1 for x, -1 for y. It's right here. So basically, this parabola crosses the axis at 2 and at 0, and it has the vertex here, and it opens up. So it's going to be like this. So, but my function, my piecewise defined function, it's only part of this parabola. So I'm only interested in the part of the parabola between -infinity and -1. So I'm only interested in this part of the parabola. So this is what I'm going to graph in here. So at -1 is the vertex, -1, 1, I have the vertex, and then at -2 it's the 0 or the x-intercept. So this is the portion. The first piece is just this first portion of the problem. Now the second piece is just a line. The second piece, a line with slope 1. So line x, slope 1, and y-intercept 0. Because you can think about it as 1 times x plus 0. So slope 1 and y-intercept 0. So if I graph this line, let's see, -2, -1, 0, 1, 2. So if I graph this line, slope intercept 0, y-intercept 0, and slope 1. So if I go up 1 and right 1 is here, or if I go down 1 and left 1 is here. So it's this line. So this is x. But the piecewise defined function says that the function is x only between -1 and 1, including 1, but not including -1. So basically, the portion that I'm interested of does not include this or that. So I'm only interested in this tiny portion in here. So this is what I'm going to graph in here. From -1 to 1, not including -1, but the -1 was included in the parabola. So you can imagine that I have a circle in here for the line, but the circle is filled by the parabola. And then at -1, the value is included. So I have a full circle in here. So that's my second piece. And then the third piece is just a constant linear function. So it's a horizontal line. Y equals -1. So after 1, the function is just a horizontal line. So it's just this portion. So that's my piecewise defined function. You can definitely do this straight on the graph and just stop, or draw it in here and then erase the portion you're not interested in, or however you prefer. Alright, so if you remember from college algebra, we used to identify a function graphically by doing the vertical line test. So if you have the graph of a function, or the graph of something, to decide if that graph is a function, you drew vertical lines, and if it intersected the graph only once, or no more than once, then that was a function. So anywhere I draw a vertical line, this graph is going to be intersected by that vertical line only once. So we have a function. But if you draw a vertical line through the second graph, you see that it intersects it twice. So this is not a function. So basically what this tells you, it's the definition of a function. Each input corresponds with exactly one output. In this case, one input, this input A, corresponds with two outputs. It has an output here, which is B, and it also has an output here, which is C. So this is not a function, because the definition of a function says each input has exactly one output. But how do we decide if, given an equation, so not a graph, how do we decide if, given the equation of a relationship between x and y, does that represent a function or not? So how do we do that? Well, we're going to solve for y, and we're going to see if each x value gives you exactly one y out. So for example, I have this, y minus x squared equals 2. Does this equation define y as a function of x? So we're going to solve for y. So I'm going to add x squared to both sides, and I'm going to get that y equals x squared plus 2. So if I have one x in here, how many y's am I going to get out? So for example, one valid input, let's say x equals 3, how many y's does it give you out? It will give you y equals 3 squared plus 2. It will give you y equals 9 plus 2, which is 11. So one input gives you exactly one output. What about for the second one? Can we decide if this defines y as a function of x? So let's see. We're going to solve for y. So I'm going to subtract x squared from both sides. So I'm going to get that y squared equals 4 minus x squared. I'm going to solve for y, so I need to take square root of both sides and not forget my plus or minus. So when I take square root of y squared, I'll get that y equals plus or minus square root of 4 minus x squared. So let's see now. One valid input. What would be one valid input? X equals, well, notice that x is underneath the square root, so I need to give it an x that will keep this quantity positive. So let's say x equals 1. X equals 1, that will give you y equals plus or minus 4 minus 1 squared. That will give you x equals plus or minus square root of 3. So you see one input gave you how many outputs? 2. So not a function. The first one, yes, was a function. So this is how you decide if y is a function of x. algebraically. Graphically, you just draw a vertical line. Algebraically, you solve for y, and you make sure that for one input, you have exactly one output. All right, so let's practice a little bit. Does this graph represent a function? Well, it's a graph, so to decide if it represents a function, just draw a vertical line. So if I draw a vertical line, it intersects it once. If I draw a vertical line here, it intersects it once. A vertical line anywhere, it intersects it just once. So yes, it is a function. It is a function. And what kind of function it is? You see we have these pieces, so it kind of tells us that it's a piecewise defined function. Piecewise. Let's try to come up with a formula for it. So let's call it f of x. So let's look at this piece, first piece, for example. What are the x values between? Between 0 and 1, including 0 but not including 1. So one of the pieces is between 0 and 1, including 0. So you see how this full circle in here, but not including 1, you have just a circle. What is the function in here? It's a horizontal line, right? And what is its value? It's a horizontal line passing through 0. So the function is 0 between 0 and 1. What about the next piece? When x is between 1 and 2. So when x is between 1 and 2, not including 2, but including 1. So not including 2, including 1. What is the function there? Well, it's a horizontal line with value 1, so it's 1. And so on. When x is between 2 and 3, not including 3 and including 2, you'll see that the function value is 2. And similarly on the other side, when x is between -1, between 0 and -1, the y is -1. So if I go on like this piece, y is the function is this. This is actually a famous function. It's called the greatest integer function. And it's denoted like this. So instead of writing all of this stuff, you just write x in a set of 2 brackets. So if you see this is what it actually means. I would rather write this than write all of this stuff. So for example, why is it called the greatest integer function? If I want to calculate what is f of 1.5, if I look at 1.5 is in between here. What is its value? It's 1. What if I look at f of 0.75? Well, f of 0.75 here, f of 0.75 is 0. So the greatest integer function gives the greatest integer less than or equal to x. So it gives the greatest integer less than or equal to x. So f of 1.5, what is the greatest integer less than or equal to 1.5? So it's 1. What if I want f of 1? What is the greatest integer less than or equal to 1? It's 1. All right, another good practice is let's do another piecewise defined function. So for this one, the first portion is going to be for x less than or equal to 0. And for the first piece, the function is just going to be the line with slope -1 and y-intercept 0. So it's going to be here at 1. If I go down 1 and to the right, down 1 to the right 1, or if I go up 1 to the left 1, it's going to be this. This is -x. So -1, 1. But I'm only interested in this portion of it, from 0, including 0 to the left. So let's graph the first portion. So just 0, including 0, and then the point -1, 1. So this is the first piece. So this is -x. And then between 0 and 3, so 1, 2, 3. So the second piece, between 0 and 3, it's a parabola down. What would be the x-intercepts? Well, 9 minus x squared when x is 3 or -3. And then what is the vertex? So the vertex is -b over 2a. But what is b in this case? So I have 9 minus x squared. There is no x in here, so this is the same as -x squared plus 0x plus 9. So b in my case is 0. So the vertex is going to happen when x is 0. And what is the y value when x is 0? When I plug in x is 0, I get that the vertex happens at 9. So the vertex is at 0, 9. And then the y-intercepts are -3 and 3. And the parabola opens down. So it will be like this. But I'm only interested in the portion between 0 and 3, not including 0, but including 3. So I'm only interested in this portion between 0 and 3. So I'm only interested in this portion of the parabola. But I'm not including the value for when x equals 0. So I'm going to have a circle when x equals 0 and a full circle when x equals 3. Okay, because of this. All right. 9 is off the charts in here. Let's say that this is 9. Sorry. Let's say 9 is here. So I'm going to have a circle at 9, and then it's going to cross at 3. And then full circle at 3. All right, and then the last piece, piece number 3, is a line x minus 3. So with slope 1 and y-intercept 3. So let's graph this quick. So at -3, I have my y-intercept, and then slope 1. So if I go up 1 and right 1, I'll be here. Up right and right 1, I'll be here. Up 1 and right 1, I'll be here. Two, 3. So this is 3 right here. Sorry. So it will be like this. But I'm only interested in the portion after 3 and not including 3. So basically I have a circle and the arrow going all the way up at 3. But the circle is filled by this parabola portion. So that's why I'll have it full in here. Okay, so that is another example of a piecewise defined function. We say that this is not continuous. So a function is continuous if you can draw the graph without lifting your pencil. For now, that's what we're going to call it. So if I can draw the graph, well, I have to lift my pencil. So this is an example of not continuous function. We will talk more about this another time. All right, one last example. Practice find the formula for the function and state its domain and range. So we are given the piecewise defined function, we see that we have 3 pieces, and I want us to come up with a formula. So what's the first piece? What are the x values for the first piece? It's everything below -1, including -1, since I have this full circle now. So the first piece is for x less than or equal to -1. What is the second piece? The second piece is between -1 and 2, not including -1 and including 2. So not including -1 and including 2. And then the third piece is everything greater than 2, but not including 2. Okay, so what is the function when x is less than -1? Well, it's just a horizontal line that would have the intercept at 2, so it's just y equals 2. What about between -1 and 1? It's a line. Well, what is its slope and what is its y-intercept? So it's the slope is, the y-intercept is 2, and the slope will be like, if I go down 1 and to the right 1, so the slope is -1. So it will be mx, so the slope is -1, -1x plus the intercept is 2. So -x plus 2. And then the third piece is a horizontal line at -1, right? This will be at -1 if it continued. So -1. All right, so that's good for now. We will practice more later, and you get to practice more in the homework. So this concludes lecture 2.